Okay, so today, today I want to talk about generalized linear inverse reconstruction. So later on in the class, I'm going to talk quite a bit about something called grappa, which is it's a kind of way of undersampling the data and reconstructing it. It's kind of, in some respects, it's kind of, you can think of it as a little bit of a hack, but it's a very effective hack that's very widely used. And so today, what I'm going to talk about is it's not the most practical way to implement a general linear inverse, but it sort of puts the reconstruction problem, it sort of rephrases the reconstruction problem just as a linear inverse, and so you can sort of see how to incorporate all different kinds of imperfections in the recording process. Because so if we just put our standard sort of Fourier picture, so the idea is we've got a signal. So I'll put this in a different color just for change of pace. So we've got our signal, and that's our complex valued signal, and in just 1D, that's the variable there is spatial frequency in the x direction, and that equals a sum over the whole object, which is done by the so what we're writing here is a Fourier transform as performed by the magnet, and it's not the exact important thing to remember. This isn't the exact Fourier transform. The exact Fourier transform that we're drawing here is not actually exactly what the magnet does. So this is the idealized representation of what the magnet does. And so it takes the brightness, proton density basically, of the image at each point, and then each data point consists of these spatial frequency samples. Okay, x times x summed across the entire image. And so what's doing this part is these are the stripes generated by gradients. But these are perfect stripes that I've drawn here, but the ones that the gradients generate aren't perfect. They're sort of slightly bent up and distorted in various ways. So that's an idealized representation of what the magnet does to generate the data that we collect. And then our reconstruction is then simply the inverse Fourier transform, which is basically exactly the same thing, except that we're now going across all spatial frequencies. And then we have our, and if this was perfect, this guy would be a real, it would be the same real image that we started with. In real life, it isn't. This one, however, is definitely a complex valued one, and this is just basically our data. And then we're doing the inverse Fourier transform, which is basically the same as the forward Fourier transform. We can reverse the x and kx. And then for every spatial frequency. So here's the data that we got out of the magnet. We just put that right down here into the Fourier transform and inverse Fourier transform it. So what is the sort of general linear inverse method designed to do? So the plan is, so one way of thinking of this, you can think of this as the, this is the signal equation. But if we think of it from the point of view of sort of a general linear approach, you could think of this as the forward solution. So we'll talk later about Eeg inverse. So the idea is that in EEG you've got some sources, they generate signals on the scalp, and then you have an inverse problem, which is given those signals on the scalp, how do you get back down to the sources? So this guy is the signal equation, and then this is the recon equation, and that's basically the inverse problem. So what we can do is we can sort of just write this out. If you look at this equation here, this inverse and forward solution, you can just write this out as a simple linear matrix multiplication. That's really all it is. How would we do it most compactly, like the mathematicians would like? So they would just say, we've just got a signal. How would we write out the forward solution? We would write it out as just a signal vector equals a matrix of Fourier coefficients times the image vector. So it's just basically, AX equals B. So it's just a vector equals a matrix operating on a vector. So you might immediately say, well, how could the image be a vector? What if it's a 2D image? So the way that would work. So you could, if you just had a line, you could imagine representing a line. Like if your image was just a line of brightnesses across a line, you could imagine representing, each entry in that the brightness of the line as one of the components of the vector. So if you had a line of 10 long, that's a 10-dimensional vector. But you could do the same thing with a 2D image. And so how would you do that? Well, you would just, so here's your 2D image. You would just sort of, string it out into, something like that. So you would just get a really long, so if it was, 256, or say 64, pixels wide, times 64, you would just have, 64 times 64 entry vector. So you could just make, so this guy, this image could just be turned into a single one-dimensional vector just by unwrapping all the lines of it. And or this K-space. And so that would be, so this guy would be for, the S vector or the image vector. But now we have to sort of say what we put into the Fourier matrix. And that's where we can essentially put in an imperfect Fourier transform. So that's basically the idea. So let's write this equation out sort of a little more detail. So if we have a column vector here, so here's our column vector of our K-space. This is basically K-space, so I should label this. So this is K-space. And this guy is the, brain image. And we could do this, you could even do it for 3D. You could make a really long vector that would basically be a three-dimensional representation. We'll just talk about the 2D version of it. So here's that column vector. So this equation is the column vector is equal to this Fourier vector. So this guy, Fourier matrix. So here's our Fourier matrix. It's a whole matrix of numbers, and then that is rotating and scaling our image vector. So there's the image vector. So what are the dimensions of this vector? So the columns of the vector are basically, x, y, going in this direction, because we've unwrapped x, y into, so that's the first line, second line, etc. So it's all of x, y going in that direction, and then what's going in the other direction? Is basically, if we do a two-dimensional one, is k, x, y. So what does that actually look like? So what we want to do is, how do we get one entry? One entry. We'll just take, one entry in this. Say, like, how do we get this entry in the matrix? And so, in this case, so basically this thing right here is our matrix. And why is this a matrix? Well, it's sort of got two. You could sort of think of the rows and columns as these two variables right here. So this guy's only got one. The image is just a function of where you are in the image. But this one has two things in it, and the x is varying here because you're summing across the whole thing, but you have to do this sum for every k, and so that thing is a bigger. So this thing here is kind of a bigger thing than this thing. So what we can do now, when we look at what this does, this generates perfect spin stripes. So the gradients haven't generated perfect spin stripes, but we're modeling it as if they generated perfect sinusoids going across, or perfect complex valued numbers going across the actual brain. But now what we want to do is actually be able to build in imperfect stripes. And to do that, so one of the problems with these more generalized approaches is that this approach is relatively simple. We try to make the gradients as close to perfect Fourier terms as possible, and then we just kind of forget about it, and then we just do a perfect inverse Fourier transform. If we're going to actually try to insert non-perfect data, we've got to get it from someplace. And so one of the biggest problems of this approach is you need to do extra scans, because if the stripes are slightly distorted from the fact that there was a B0 problem, well, then you've got to measure the B0 problem. If the gradients weren't quite linear and so they were causing the stripes to curve, then you've got to measure the gradients and put that in there. And some of these measurements, like the gradients, are known in advance. So when you design the gradients, you try to make them as linear as possible, but if they're a little curvy, you can actually measure what that is once and for all, and then you can just use that. So some of the additional information that we add is relatively easy to get, or it doesn't change across scans, but other things change across scans. So if you put somebody in there and the B0 field is messed up, then you're going to have to try to measure what happened to the B0 field. And so and so those, so this thing, this number, this complex number that we're going to put in here, so these are complex valued entries. So each number in there is a complex number, because each one of these guys for a given kx and x is a complex number. So so this complex valued number is going to be a function of where you are in x and y, but also when you recorded the data point. And so why does that get in there? Well, the problem is, say the B0 field is a little off. What that means is that the precession frequency isn't exactly what you thought. That means that the phase is going to be slightly different than what was predicted by these perfect stripes. But the phase is going to be dependent on how long after the initial RF pulse you essentially filled in that particular this particular data point. And so it's going to be dependent, and the reason for that is that the longer after the initial RF pulse, there'll be more time for the phase to get further ahead or behind, depending on what the local B0 is. So time is going to be in there too. And so what are the kinds of things we can imperfect things we can stick in here? So one of the things is we can put in the gain of the RF coil. So this is a function of x and y. So it turns out if you have coil gain. So what is that? That would be you've got the brain here, and then there's a coil somewhere over here like that, and it's going to be brighter where the coil is. So how could you measure that? So an example of how you could measure that is you could record an image, a quick and dirty image, from the body coil. So the body coil can stimulate the spins, and the body coil is often used to stimulate the spins even when you're recording from the brain, because it has a very uniform RF field. And then you record the signal coming from the local coil. But what you could do is you could record a signal, take a quick and dirty image through the body coil, and that one would not have any fall off dependent on the coil. And then you could calculate from that, and then take another image from the local coil and look at the ratio between them and figure out how is this thing modifying the signal. And so that's one piece of information, sort of imperfect. An imperfect Fourier transform is going to mess up the amplitude of your signal depending on where you are. So that's the coil gain. So that's one thing we stick in there. Now the coil may have some kind of phase problem. So we might have to put in another number, minus I, some phase, and that phase is a function of x and y. So the coil itself will introduce some imperfection in recording the phase of the signal coming from different parts of the brain. And so so remember this number here, this single number that we're calculating is basically for a particular spatial frequency and a particular XY point in the brain. So this number is going to be different at each one of those XY points in the brain. And what this would do is, again, these are imperfect. These are actually sort of building in the actual imperfect stripes that the gradients are generating, rather than just assuming that they're perfect, the way we do when we just use this forward solution. So that's the coil phase, sort of coil phase. We could put that in there. we have to measure it by some additional scan. And now we've got some T2 decay. Now that's another thing. So this, if I'm doing this for, for example, an EPI scan. So we haven't talked about what an EPI scan is. This is like recording all the lines of K-space in one shot, typically. But if we, just as an example of what it might look like, there's gonna be some T2 decay. So it's gonna have here's the time of one readout, and this is what particular readout line we're on, because this T2 decay is going to get more and more as you continue down the K-space, because you're recording parts of K-space at different time points, which means there's different amounts of T2 decay. And then we're going back and forth across K-space, and so then we have to also consider what point in K-space we're at, and this is the readout time step. So this is the readout point times the readout time step. So like how far to the left or right of K-space are we at? And then we also have the echo time in there, because there's some time before we begin to record the data, and that whole mess divided by T2. So now the question is, where did we get T2? Where did T2 come from? So then we'll have to make some kind of estimate of T2. Now that's, you could take just a very coarse estimate of T2 across the entire brain and use that. It'll be better than assuming that there was better than not accounting for this. But this is basically, actually consider the T2 decay. So like when we were talking about fast spin echo, we just said, we just blow off T2 decay, even though the different echoes in the echo train have different amounts of T2 decay, so that different spatial frequencies are recorded with different amounts of T2 decay. So obviously that's going to mess up, the Fourier transform a little bit, because it's not taking that into consideration. So we could take that into consideration. That's how we would do it. Multiply by another E. And then the one I was talking about before, what about the B0 error? So the B0 error is going to be another. So remember, these are two different things. This guy is a complex number, and when we multiply by a complex number, we're causing a rotation, a phase rotation. So this guy, phase rot. Whereas this guy is just real decay. So this guy's a real number, and when you multiply. So when you multiply by this, it makes this f smaller. When you multiply by this, it rotates the angle. It rotates the angle of the complex number. This guy's a complex number here. So now we're going to multiply by another complex number, because we're going to deal with the B0 error. And so the B0 error is going to be e to the minus I gyromagnetic ratio times whatever this B0 offset is. So here's our B0 offset. But the B0 offset is going to, vary at different points in X and Y, which we would try to have to measure. And then it's also going to, vary by at what point did you collect that K-space point. So that's how long it takes to do one readout. This is whatever readout line we're on. And then, plus or minus, depending on whether we're going back to the left or right direction in K-space, times the readout time point. So this basically is, and this requires trying to measure what the B0 defect is. So we'd have to do another quick scan. So this is B0 error. So we have another quick scan in order to figure out what the B0 error was at each point in X and Y. It doesn't have to be, the B0 error generally tends to vary relatively slowly, and so we don't have to do a very high resolution scan necessarily. It doesn't have to be exactly the same resolution. Or if we're doing echoplanar imaging, that's already lower resolution. And then, so these are all just corrections, and then now we have to actually, actually do this. We have to do the phase encoding. And so, so here's a non-ideal version of the phase encoding. So it's going to be, whatever. So this is basically our X and Y Fourier transform. But we could also, one thing I haven't put in here, we could also insert some XY, yet one more thing. So the gradients are not completely linear. So XY gradient nonlinearity. Could also add. So we could add this, in here, because that's one gradient, and then we've got another gradient in here. So what is that? So that just means, like, when you turn the gradient on. So if I turn the gradient on, it's supposed to be like that. It's supposed to be just like a increase in the BZ as you move, say, in the X direction. But in real life, when you get closer to the gradient coils, it tends to be a little bit bent like that. And that number is known, and so we could insert that in here too. So this basically is the frequency and phase encoding. And then finally it's a discrete Fourier transform, so we're multiplying by our delta x, delta y. That's this guy here. So this is the entire mess. And so what this does is this represents all these imperfect stripes. So one thing to remember about this is we can't do, we're still using physical gradients. And so the gradients, what do the gradients do? They just make stripes. Now, they don't make perfect stripes, but they can't make sort of like, star patterns or something like that. They basically, the only thing they can effectively do, a linear gradient, is make stripes. Maybe not good stripes, but stripes. So this isn't completely general. We can't make any old phase pattern in the brain. We can basically just make stripes. And so what this is this is the tedious way that we calculate these imperfect stripes that our gradients made. So what we've done so far is the forward solution. So what we've done is we've replaced, this simple Fourier equation, we've replaced it with this matrix multiply. Our k-space signal equals this square matrix of Fourier coefficients times our image vector, and except now we're doing like an imperfect Fourier transform. So this thing, if we took out all these correction things and replaced this back with our original thing up here, kxx, kyy, kxx plus kyy, then you're going to leave out, probably left out a 2 pi in there. Yeah, let's put that back in there. minus I 2 pi, there we go. Then we would just get back, so if we took out all these guys and took out all the mess here with the gradient nonlinearity, we would just end up back here. So now what do we do with that? So now the plan is we have to invert it. So what is that? So I'm going to erase. I'll erase the. So this guy just be one last. So this guy, corresponds to one. How to calculate 1 point in that matrix. So that's. So we just do this however many, 4,000. If you're doing a 64 by 64 EPI scan, there'd be 4,000 numbers to calculate here, and presumably from various pre-scans. So eventually something like this already happens to some extent, but it's going to happen more over time as scans are further optimized. And how will this work? Well, there'll be a bunch of quick little pre-scans built into the whole scan. And so, that's how you could sort of practically do something like this. There's already pre-scans, built into the scans that we talked about, but you would just extend those a little bit. And so then you would end up with like a single scan, but it'll have like, three quick and dirty calibration scans embedded inside of it. One other issue that's always a problem whenever you make something more complicated like this is that, like, what if somebody moves during the calibration scans? And then we have to have some kind of, movement artifact, because if they move during the calibration scans, that could sort of mess up the whole rest of the regular scans. So, but that's just the way, unfortunately, the way the world works. It's very similar, I mentioned last year, so very similar to biological evolution. So when you look at biological evolution, why is it hard to figure out? Well, it's just had so much time to optimize things, and once you make things extremely optimized, it gets quite tricky to figure out how they work, and that's exactly what's going on here. This is very simple. Just the Fourier transform is very simple. These other things have all different kinds of complex dependencies, and making them actually practical so that they don't actually make your scan worse is actually very difficult. So in my earlier days, I would have thought, just do it this way, because this is the right way to do it, because it actually incorporates all the information. But in practice, what you find out is that the example that I gave you, what if somebody moves during the calibration scan? Now the rest of the scan completely depends on the calibration scan, so you've got to have a whole bunch of sanity checks to make sure that the calibration scan didn't go bad. Like maybe stop the scanner and say, like, no, the calibration, you moved during the calibration scan, so we've got to do that one again. Okay, so now we got to invert it. So how do we invert it? So if we just write out I've got it up there. So there's our forward solution. So our inverse solution is basically just we'll do a pseudo inverse, because we're going to end up with rectangular matrices. So basically all we need to do is just find the inverse of the F matrix. So the F matrix with all those Fourier coefficients in it. So here's the signal. Ignore that for the time being. Here's the image. What we want to find out is what is the inverse matrix that is basically the inverse Fourier transform. So what is the matrix that we can multiply the k-space data by to get our image data? So it turns out if we've got multiple coils, this will be overdetermined. And so we'll end up with a rectangular matrix. So what would that what would that look like for just 2 coils? So if we just did, you could put 32 coils into it. But if we just did it for 2 coils, what's going to happen is we'll get a longer k-space vector. So here's coil 1 and here's coil 2. So this is kx going down this way, but we've got kx going down this way again, more kx. So we'll have two globs of data from the 2 separate coils, and that will be so this is our signal, still our forward solution, not this guy. So here's our forward solution. So this guy is coil 1 and coil 2. So then we're going to have to make a bigger F matrix. So this guy is the inverse. Make sure we're, and this guy is a forward for 2 coils. So we're going to have to make a bigger F matrix, and so the F matrix is going to have all those F coefficients for, so here's F matrix for coil 1 and coil 2. But the image that we're going to reconstruct, there's only one of those. So because here's the XY coordinate of the of the matrix. We put those in red so that they don't get mixed up with the matrix themselves. So this is our KX XY and then KXY again. This is our XY, and this is XY going this way. And then this is KXY going this way, and again. So what this is, so we've got an image that's sort of being turned into a larger amount of data, multiplied by the number of coils. So when we try to invert it, that's a good thing. It's a good thing because we have more data. That's why we say it's overdetermined, because we've got more data that we're using to try to reconstruct this thing. So when we do this inverse, there's a couple different ways of writing it out, and so we could write out the inverse, this pseudo inverse, which is it's an inverse that will work with a rectangular matrix. So we could either write it out as the transpose of the matrix times the matrix inverted times the transpose of the matrix. And there's another equivalent way of writing it out, which is the transpose. You'll see one of these is much worse, times the matrix times its transpose. Got to be an inverse there somewhere. Yeah, there we go. I didn't put the inverse in my. Let's put a note in my notes. Okay, so what is that actually? Why is one of these are mathematically equivalent, but one of them involves a lot more numbers, and so we don't want it. So if we look at the first one, it looks like so the transpose of this guy, that just means sort of swap the rows and columns, is going to be sort of a long rectangular matrix this way. So that's FT. And then we're multiplying that by a rectangular matrix this way, which is F. That's our original F. and then we're taking the inverse of that. But the good thing about this is when you multiply two rectangular matrices like this, you get a square matrix, a small square matrix. And then we multiply that small square matrix times the transpose again, and we get a nice, and that makes more numbers, but the main problem is this is expensive. This part, doing this is, computationally expensive. So this is computationally easier because it's a square matrix. Whereas if you look at this other case, so that was this guy. If you look at this other case, what does it look like? It looks like the transpose of the Fourier coefficient matrix times a column matrix, because this is the F, times we have a matrix that's longer in rows, multiplied by one that's longer in columns. And unfortunately, that when you do this matrix multiplication, you get a square matrix that's square in the long axis, and so this one is much worse. Yeah. Worse. And how much worse is it? It's like it's really worse, because basically this inverse is inverting something that has x times y squared. This inverse is inverting something that has x times y times coils squared. So that's going to be really way bigger. So if you've got 32 coils, it's going to be, the number of x points times the y points, that might be 4,000, and then you multiply by 32. So it's going to be, and then you square it. So it's going to be gigantically bigger. So it makes a really big difference. You would do it this way. And so the idea, this guy's called a Moore Penrose inverse. So what's the bottom line? So the bottom line is we would for each slice, we would have to collect all those pre-scans, use the equation that I erased to fill in all the components of this F matrix for a particular slice. Then we would do this thing to it. We would do this thing to it, as opposed to this bad thing. And then we would end up with this guy. And so once we got this guy, then so this guy goes over and generates this guy. Once we have that guy, then we just have to do just a simple matrix multiplication. We just multiply our signal that we got times this, and then we would get a better image. So this is the absolutely most general way. So if you look at something called sense, that's an example of a semi-general reconstruction. And there's many other ways of undersampling. So these are some of the words you might want to. So undersampling. So if we undersample the data, so one of the things you could use with this method is, what if we just sort of leave out some of the data? So we've got 32 coils, and so it's way overdetermined, and so we should be able to strategically leave out some of the data. And so there's a method called compressed sense. Compressed sense, which is a method of trying to figure out what is the what is the data what's an optimal way of leaving out the data that still gives us a pretty good image. And if you look up things in compressed sense, it's possible to actually, you can leave out, say, 3/4 of the data and still get a pretty good image. And so that's based on a general linear inverse approach like this, but with a bunch of optimizations and tricks to not have to invert this gigantic matrix too many times. So I didn't give you anything really practical. I just wanted to really sort of emphasize that you could just view these Fourier transforms as simple linear matrix multiplications. Just case-based data vector equals just a matrix of fixed coefficients that you get from this. These are all in the Fourier transform. These are all fixed, and you can calculate them in advance with no trouble. And then operating on your image vector, which is just like, say, an XY image strung out into a long vector. And once you phrase it this way, then you see it's basically just a linear inverse problem, and there's a lot of tools for dealing with these kinds of problems because they're used in all different kinds of fields. And it's actually an overdetermined inverse because we actually have more data than the data that we're trying to reconstruct. That's a good thing. So the more coils, the more overdetermined it is. And so then you can actually use this approach to find ways of sort of doing something that's like a Fourier transform, but might be a lot more efficient and you might be able to get away with recording a lot less data. So that was just an intro to it. It's a big field, and I don't understand lots of the field, but you could look up sense, undersampling, compressed sense, and get an idea of what's out there. Okay, David, I think we're done for recording.